All right. Hello, everyone, and welcome to today's Corundum developer meeting. Um, I just got status updates for today. Not a whole lot new because getting some of these new boards working and getting some kinks worked out has been taking up quite a bit of time. Anyway, let's see. The main points for today are, new device support. I basically pushed everything that's mostly working into the repository for now. The only things I haven't pushed yet are, I think, the 100 gig design for the Stratix 10 DX because that one doesn't build yet due to, some issue we're trying to figure out on the Intel forums. Everything else is up, but on the basically the Stratix 10 DX and the Agilex, everything with the E-tile, the PTP support doesn't quite work right yet. So that's a to-do to fix at some point. User space tools, I added a new one. Somebody was asking about it, so I decided to sit down and do a bit of reworking and clean up, try to add some additional checks to make sure that it's going to be somewhat more useful and somewhat safer to use. So I went ahead, that's in the repository now, and did some testing to make sure that everything is doing what it's supposed to do. So a little bit more details on that in a minute. I've also been making quite a bit of progress on the PCIe flow control shim implementation. I think I still have some tweaks that need to be made to that, but that should be done hopefully this week. And then I'll go ahead and push everything up to the main Corundum repository. So definitely a bit it's been a while since I've done that. So but there's been a lot of changes that I've needed to verify across multiple different boards. So but yeah, that'll be happening pretty soon. And then then the carryover to do items, and mainly in terms of the variable length descriptor support, that's going to be the next thing that I take a crack at once we have the flow control support finished off. All right, so getting on to the new device support, the bitware 250 SoC support that has been added to the repository. The Stratix 10 DX dev kit, I've added a 25 gig design that can be configured for 10 gig as well. 100 gig design for the Stratix 10 DX currently does not build yet. There's some sort of an error associated with the E-tile that I'm running into. So once we get that sorted out, then I'll add that one as well. I mean, I guess I also have to get it to close timing as well. We'll see about that. The Stratix 10 is quite a bit slower than the Agilex in terms of the fabric logic. And then I also have the Agilex designs. I've basically gone ahead and added all of those. This is the Stratix or the Agilex 10 or the Agilex F014 on the DE10 Agilex. And I have designs for 25 gig that also has a variant for 10 gig and 100 gig. So basically the same as most of the other stuff in the repository. As far as the interfaces on there on the P-tile, the shims are basically working. The flow control I don't quite have sorted out yet. I took a crack at that over the past couple of days, and well, it didn't hang, but it didn't really improve the performance much. But I think I have I may have discovered what the problem is, and it's completely unrelated to flow control. I had some parameters in the config.tcl that didn't match the Verilog parameters that I was using during simulation. So in simulation, you get 100% throughput on the PCIe link, but in hardware, it seems like it was limiting performance quite a bit in a couple of aspects. So I need to build a new design with those parameters updated, and I'm also going to revisit those same parameters on the Xilinx devices as well, because I think the particular values that I'm using for those dated back to basically before flow control was implemented in an effort to avoid headline blocking. So I have a very low limit on the number of in-flight writes. Basically, it won't issue any more than, I think the setting is 3 writes for most designs until it gets a transmit completion sequence number from the hard IP core. And when the DM engine is directly connected to the IP core, then that's fine. But when you add FIFOs and more pipeline delays and whatnot, that's going to affect the throughput. And if we're looking at the flow control credits, if that works correctly, then I don't think we need to have a limit on there at all, or we can set the limit a lot higher. So um, that was definitely causing problems on the, or I think that's the main cause of the problems on the Intel devices, and it may also be limiting the performance on the Xilinx devices. So I'm going to make those changes and build some new designs over the next couple of days and see if that changes anything, because that could significantly improve performance, mainly on the RX side and in terms of writing descriptors back into host memory. So yeah, that's that. Let's see. And then in terms of the e-tile support here, 10G and 25G are basically doing what they're supposed to do. PTP has well, in terms of throughput, PTP has some problems on these. There's some weird issue where if you saturate the TX direction, then RX timestamps get screwed up, which makes absolutely no sense. I suspect it's either an issue in the p-tile itself or hopefully in the soft logic around the p-tile, but if it's or around the e-tile. But if it is an issue in the e-tile, then PTP is just not going to work on the e-tile devices. Or at least you're not going to be able to get timestamps for all packets, and we'll have to jump through some hoops to actually implement it so you only get transmit timestamps for PTP packets, which is kind of screwy. I have a post on the Intel forum. We'll see if that if we can get to the bottom of it. Let's see. PTP right now does not work at all on the 100 gig version, but there's a whole sequence you need to do for calibration to make it work. Haven't implemented that yet. We'll do that from a soft core at some point. But you can send and receive data, on the data path. So we'll start with that. Yeah, mainly just getting the core data path working, at high bandwidth is the goal with these designs. Right. So that's the new device support. Then I also added a new transceiver control user space tool. Well, it's not really new. I've had the code lying around for a while, but finally got a number of issues, worked out of it. It's intended for transceiver control and debugging. So all of the designs, all the 25G designs, if you want to reconfigure those at runtime for 10 gig, currently this is the only way to do it. Eventually, this particular bit of functionality, the idea is to push that into the software, and then the driver can basically ask the software to load particular presets. Well, not really load presets, to run the link in particular configurations, and then the software will do what it needs to do in terms of talking to the transceivers. So currently it supports GTH and GTY transceivers on ultra-scale and ultra-scale plus parts. Potentially this will be extended later. I don't think it'll be too hard to add support for the H-tile and potentially E-tile as well on the Intel devices, but there's a few more pieces that are going to be needed for that to work. So this can load profiles for both 10 gig and 25 gig, and for DFE and LPM equalization. I also went through and I extracted all of the parameters for these either 2 or 4 presets, depending on the transceivers. So the GTHs only support 10G, so you can switch between DFE and LPM, and the GTYs support both speeds. So there's basically 4 presets you can load. I have some TCL scripts that I put together to extract those parameters. It's pretty simple if anybody else is interested in doing that for some reason. The way this is done in the tool is still kind of rudimentary. It doesn't really do a whole lot of checking besides tries to figure out if the PLLs are set up such that you have a either a single 10 gig PLL or QPLL 0 running at 25 gig and QPLL 1 running at 10 gig, and then it'll allow you to load the corresponding profiles. But if you've changed other aspects about the transceiver configuration in a design, it might not work correctly. So word of warning, it is not the smartest tool ever, but it does do a few things if you're running the transceivers more or less in the default configuration. The other thing that you can do is you can run iScan measurements, and this is potentially quite useful for debugging, because you can look at the link quality at a pretty low level. And it also supports running concurrent measurements on multiple channels. So if you have like 4 or 8 transceivers or whatever, you can use this tool to run iScan measurements on all the channels at the same time. And I also added a script which will take the raw iScan data and plot a nice little heat map. So I went ahead and collected those for a couple different on a couple different boards and a couple different configurations. So here's a couple iScans that I collected um, on a Kintex UltraScale part. So this is on the Nexus K3P-Q board with a 2-meter DAC to a Mellanox ConnectX 5 card. So I used the user space tool to reconfigure the transceivers with the 4 different presets, and then captured iScan measurements with all those presets. So this is 25 gig with DFE. This is 25 gig with the linear LPM. This is 10 gig with DFE, and this is 10 gig with LPM. And the thing that I find quite interesting about these results that was rather counterintuitive is that the DFE seems to be producing a much smaller eye than the LPM, right? So this is like the 25 gig LPM versus the 25 gig DFE. I don't know why that eye is so much smaller. And same thing with the 10 gig, right? The DFE eye is, I mean, it's about the same height, I suppose, but it cuts off all of the corners, right? It's much more angular. Not sure why that is. It would be interesting if anybody knows more about how equalizers work, just to get some sort of a sanity check that these things are doing what they're supposed to do. This one in particular seems like way too small compared to some of these other ones. I mean, you would expect LPM to make a smaller eye than DFE. Although maybe I guess you need a longer cable, or more jitter or something to close the eye. So I don't know. Maybe this isn't the problem, but to me it seems a little on the small side. So all the vertical and horizontal scales and whatnot on all these are exactly the same. The only thing that has changed is the configuration of the receiver in terms of the equalizer settings. So yeah, I don't know. It's a bit of a head scratcher, but there you go. The tool works and it's now in the repo, so anybody that wants to poke around with it, it's available. All right, and now moving on to the flow control stuff. So with the new shim implementation, with the addition of a whole bunch of FIFOs, the handling the flow control in the DMA engine doesn't really work because of just a delay between when you send a TLP and when the credits are actually consumed from the standpoint of the credit counts of the DMA engine. So that really made flow control, essentially completely ineffective. So what we have to do is handle that in the shim itself, where we can react more quickly and exert back pressure against the DMA engine instead of having the DMA engine just, not send something. Now that we have the FIFOs, we can exert that back pressure. On the UltraScale, I have it implemented, and it seems to be working. I have a plot that I'll show in a second that shows, the effect of that. On the H tile, I think I have it implemented. I just noticed that the test case is hung in the repository, so I need to go figure out what file I forgot to edit, or figure out what's going on with that. But it seems to be running on the H tile. One thing I need to do is confirm that it's actually improving the performance, because I don't have a 100 gig design on the H tile, and the 25 gig design that I do have didn't close timing in the max when I built the design over the weekend. So I need to do some more testing there and verify that it is in fact providing an improvement. And then on the Agilex design, I was seeing low performance, I think because of these other changes, or because of these other parameters in the config.tcl file, and it didn't have anything to do with the flow control. So I think I have it working on the Agilex, but I need to do some more testing to verify that once I change the other parameters and see what happens there. The important thing, though, is the design that I have loaded on the Agilex, it doesn't hang. So that's good. And that implies that I think I'm doing everything correctly in terms of flow control. The reason the Agilex is a little bit different um, is it reports limit values out of the hard IP core instead of available counts. And the way the flow control counts in PCIe work is they continuously increment and then overflow. So the limit count, it just increments and increments and increments. And to figure out how many are available, you got to do some, additional accounting to count up how many things you've sent, and you got to count them up in exactly the same way that PCIe counts it. Otherwise, these counts diverge. And the other problem is that the hard IP core occasionally sends its own TLPs, which consume credits, but you can't see those. So you got to jump through some additional hoops in order to do the accounting properly, because you can't see you can't see what credits the core is consuming, but you do see the credits that the core consumed getting released. So if you don't do something, then those numbers are going to diverge to a point where you're going to think you don't have enough credit, and then it'll hang. So I implemented it. It didn't hang, so I think it's working, but I need to do some more testing to verify that. And then I also need to adjust these parameters in config.tcl so that it actually tries to run at line rate. Because right now, the RX performance is not so great. But yeah, I think that's a combination of this write count limit, limiting it to like 3 operations, in combination with the higher latency of the FIFOs and the MUX in the shim. So yeah, with that count lifted to a higher value, then it should, I think, perform better. All right, so let's go take a look at some performance metrics real quick. So these are the ones that I showed before. We have baseline 1500. This is before the segmented interface and with the flow control with the old shim. So probably the more interesting curve from here is the 9K MTU curve. So this, you can see that these guys max out at around 95 gigabits per second, something like that. There's definitely a significant gap between this and line rate, which is like 99 point something for MTU, for jumbo frames. Right. So then we go ahead and switch over to the segment interface. And so this only goes up to 8, so can't really directly compare these. This only goes up to here, but this one doesn't really hit line rate. It goes up to around 80, and a TX and the RX is around like 50, something like that. But if we look at the jumbo frames, this ends up being much faster, right? This is hitting like 98 gigabits per second, something like that. It's it's getting pretty close to line rate for both TX and RX. These, that's a different story. Need to do some work to improve those. But yeah, so this is looking a lot better, right? So compare this one, these guys, this one maxed out at like 95 or something, and then comes down. This one comes up to around 95. Yeah, so this one is now basically, this one is glued to the top in terms of the TX performance. The RX, yeah, this one's glued to the top in terms of TX performance. RX performance is getting up there, but not quite hitting full line rate. But now once we implement flow control, I think they get totally glued to the top right here. So it's like if you didn't have the limit at 100 gigabits per second, right? This one would probably go off the top of the graph here, would probably exceed 100 gigabits per second, but it's being limited to the Ethernet line rate. So that's what you want to see, indicating that we are limited by the Ethernet line rate, not by the PCI Express interface. So with flow control, yeah, we can now hit full line rate. Now we need to figure out what's going on with this guy and get that guy up, and then get these guys up as well. But that's some progress. It doesn't seem to make much difference for 1500 byte frames, indicating that whatever's going on here is, software probably, or lack of segmentation offloads, things of that nature. But yeah, so for 9K jumbo frames, we can definitely see an improvement using the flow control. The other thing interesting is that these two curves here hold together quite a bit. So I guess that means things are fair sharing better when you have the flow control preventing head align blocking in one direction or the other. So yeah, that's some progress there. So this will be pushed. So the flow control for this on the Xilinx devices has been implemented. That's in my development fork. Once I get things, working properly on the Intel devices, then I'm going to push everything up to the main Corundum repository, which hopefully that'll be this week. Let's see. And then the next thing I'm going to take a crack at is the variable length descriptor support. Now that, well, once I have the shims fully squared away, then this will be next up, because this one is going to hopefully improve the timing on the Intel devices. That's one thing I've been doing actually. In addition, is a bunch of timing closure work on our timing optimization work on the Ethernet Max and the PTP CDC components to get things working at 25 gigabits per second on the Stratix 10 MX. I guess I didn't mention that earlier in terms of the board support, but I've actually overhauled 2 different board designs to support 25 gig that didn't previously support it. So the Stratix 10 MX and also the VCU 108. So you can now run 25 gigabits per second on UltraScale, in addition to UltraScale Plus, which was already supported, and on the Stratix 10 MX. And both of those required quite a bit of work to get timing closure with the PTP CDC components and with the Ethernet Max. So I've been doing quite a bit of work on the timing closure side just to get that. The next step then is to get things working on the 520N MX board, which is what we're using for the research project at Sandia. And on that, a lot of the problem is in the PCI Express side and in the core logic. So a lot of the problems there, hopefully with the variable length descriptor support, we'll be rewriting those modules and improving the timing performance by having not just a better implementation to start out with, but also implementing various optimizations to improve the performance there. So yeah, hopefully I'll be able to start working on this in the next week or two, and I'm not sure how long it'll take, but I'll definitely let you guys know as the implementation progresses. Let's see, what else do I have in here? Management software. I'll circle back to this once I get the variable length descriptor support operational. And this one, I just talked about the new transceiver application for the user space tool. So the management software is going to be responsible for loading the transceiver configurations under the control of the driver, but the software will also have provisions for talking to the user space application as well, for running iScan, and also for loading potentially different configurations that the management software doesn't have a preset for debugging applications. So that's the idea with that. And I guess also, like, for the getting PTP working properly on Intel devices at 100 gig, there's a big complicated calibration initialization routine, so that'll be handled by the software at some point. Yeah, okay. And then 10 gig, 25 gig switching. This has been a to-do item for a while. We need the software to implement to finalize this, but we now have the config tool in the repository. So if people want to screw around with this before we have the software implemented, then we have that tool so people can use that. And I think that's about it in terms of status updates here. So there's also the clock info register block. Emily was asking about that a while ago. When I have some time, I'll implement that. And then, yeah, I think that's about it. So if anybody has any questions or comments, let me know. That about rounds out things in terms of status updates. So
I want to talk about iScan. I
yeah,
also
sure.
I also tested iScan with LPM and DFA.
Mhm.
and the results were similar, but I tested with very short cables, mostly 1 meter, 3 meters, breakouts and normal 100G, but all of them had similar to these results. Maybe, as you said, it might be DFE might be good for long cables, maybe long copper cables, maybe, I'm not sure, but I also think
Right. So my
so.
understanding about DFE is that it's necessary when you have a pretty high loss. So this
Yes,
would,
yes,
I think it's more for, it's like with a DAC, they have, you know, nice twin acts going through there. But when you're going through like backplane copper traces, that could be like a bit lower signal quality, and you'll get, you know, more high frequency loss in that case. So it's probably more like when LPM can't open the eye, DFE might be able to. But if LPM can open the eye, then maybe DFE doesn't really help. So I'm not sure about that. But yeah, it's nice to know that you're seeing similar results. So, and this was, which board were you testing on? This was the that 9P part or the silicon board, or is this some different
yes,
board?
silicon. I
Okay.
test with silicon, two different boards on silicon.
Okay. Yeah, one thing I have not done yet is done any testing with like AOCs, because those tend to have retimers, CDRs in the actual optical modules. So that definitely helps with signal quality. It's like with the Intel FPGAs, particularly the well, the Agilex is the only one I've been able to test in this mode. One of the issues that I have on those at the moment is in 100 gig mode, for some reason, the soft logic in the E tile is um, not doing the transceiver adaptation loading properly. It's like something didn't get enabled that was supposed to be enabled or something. So it's only running with the default parameters. So in 10 gig and 25 gig, it does load those, does load the parameters, and it does put the transceivers in DFE mode and adjust all the gains and whatnot. And it works with the DAC. You know, 2 meter DAC works just fine. But at 100 gig, doesn't work. You can go in with the, what is it called? The system console thing in Quartus over JTAG and manually plug in all the settings, and then the link will come up through the DAC. Or you can plug it in AOC and then it'll work with the default settings. So even I have like a 30 meter AOC and it works fine because it has the retimers in the modules. So yeah, I don't know what's going on with that. It's kind of annoying. I have a post on the forum going, you know, what do I need to do to make this work? Or is this a bug? We'll see about that. But yeah, so one thing I should do is take a set of eye scan measurements with an AOC and see if that does anything. The only DACs I have are all 2 meter. I basically have a bunch of I have like several 2 meter DACs and then several like 30 meter AOCs. So and I usually just use the DACs because the AOCs, the modules get really hot.
Yes, they also have problems like that. And you know, when I first time used AOC, of course, it was very hard to to make it work first time. I didn't know about they had whole different. They didn't even have a very good, a very clear standard, and I looked at the forums and it was about some register low power mode, disabling low power mode, and I also I tried first just wiring LPM to 0, and I don't remember what else I did, and it worked. It didn't work. And there are also compatibility issues, too much compatibility issues. in
Oh boy.
AOCS, but in a deck, we used Mellanox deck for solar flare, and it works perfectly fine.
Yeah, the one thing that really annoys me about the optical transceivers is all of the vendor locking that takes place. So,
Yes,
switch
there is.
vendors are like, oh, if you want to use our switch, right? Then you also have to use our AOCs. You have to use our whatever. It's like, really, really,
They have very
and you're just not going to bring up the links if I plug in somebody else's transceiver. That's like, come on. Yeah, because they
they
look at
have
they read out the manufacturer ID from the little EEPROM, and then they
yes,
say,
they
nope.
have EEPROM, and they can write anything they want. And there was, I think, something like password to read that there is some memory, and to read that memory, I think you need password, something similar to password in the
Yeah, so
standards, and they can write anything there. Maybe they have some different password or something like that, and
yeah, I would need to take another
maybe
look at the spec. I don't remember seeing much about passwords, but it's possible if you're trying to write certain values that you need some sort of a password for that. Or if there's like, super vendor specific stuff. That's not something that I've really had to delve into. The main things that I've had to deal with in terms of optical transceivers is you have to tie LPM low and reset high, and mod cell you got to do the right thing with in order to just be able to talk to
yes,
the darn
yes, yes,
things.
exactly.
Um, and then if you're trying to run at a rate other than what it's specified for, like for the 25 gig ones, if you're not running at 25.78125, you usually have to go in and turn off the CDRs on both ends. Otherwise, it won't work. Now, something like a Mellanox NIC might be smart enough to do that. But if you have an FPGA, you got to do that yourself. So that's definitely a problem I've run into before. Is why does this work with the electrical loop back and the DAC, but not with the AOC or with the optical modules? Oh, we got to turn off the CDR because we're not running at the 25 gig rate. So yeah. And I ran into one of those where they didn't even have documentation. There was nothing in the datasheet that said anything about a CDR. So
Yes, yes, yes.
I
CTR.
was trying to get that working, and it's like everything else works, but this one dang module. What's up with that? Then this was when I was doing one of the internships at IBM, and one of the other guys was like, "Well, does it have a CDR in there?" I'm like, "Documentation doesn't say anything about a CDR." And he's like, "Well, sounds like there's a CDR." I'm like, "You might be right about that." You send an email to those guys, and they're like, "Yeah, you got to turn off the CDR." It's like, okay, would have been nice if you had mentioned that in the data sheet.
Yes, data sheets are
But at least it's a
poor.
standard register. You just write 0 to this one register, and then it turns off, and you're
Yes,
good. So anyway,
and we everyone has to use I2C for that, and I don't like. I think a customer who wishes not to use I2Cs, for some it might not be. Some customers might not want to use I2C, I think, for QSFP,
well,
because only because of some configurations you will have to use I2C.
I mean, so much stuff uses I2C. Basically, every board that you have is going to have one or more I2C buses on it for various reasons. So, yeah, it's not the
I
greatest
mean,
protocol, but it's only two pins, so
just for this QSFP.
right, yeah, yeah. I don't know. Yeah, it is a
Uh,
little annoying, but it is what it is.
I think Bob might know more about these QSFP problems, because he works in Cisco, Cisco compatible AOCs. Maybe he knows about that.
No comment. No, I'm just kidding. Well, for the products I work on, actually, we don't specifically certify, or say, we just say you're kind of at your own risk, and we have ones that we recommend for the various modules. But yeah, there's there's a huge list of transceivers and compatible optics and so on. And yeah, some are supported, some aren't. That's all I have to say.
Yeah, I mean, it's I have no problem with having a list. Like, this stuff is supported. If you use something on here that doesn't work, then we'll help you fix it. But locking
Right.
it out in the software, if you use something that's not supported for whatever reason, and then it just doesn't work because the software is like, nope, I'm not going to bring the link up. It's like, are you freaking kidding me?
Yeah, we on the products I work on in the ultralight, we do not do anything like that.
Right?
But
Yeah. No, I think
can't
it's
speak for
mainly just
rest
the
of
Switch
system.
side and the yeah.
I can't speak. Yeah.
Yeah.
I
I
know,
mean,
and then I know there's some subtle things with certain NICs or cards or how they do link up, link down, and they can cause the switch to have issues because it's expecting something behavior and other behaviors happen. So we see that occasionally.
Yeah, I guess that wouldn't surprise me because I know the Mellanox NICs are quite good at figuring out the right link rate to run at if you don't have auto negotiation enabled, right? I plug in an FPGA that just run at 25 gig of no auto negotiation, no FEC. You know, the NIC figures it out. I'm not sure exactly what they're doing. They must be just testing multiple configurations until they find one that works. But I can definitely see that, you know, causing problems. If you have two devices that are trying to do this same kind of just try it and see what works sort of thing, they could end up in the wrong state.
Right.
So yeah, I could definitely see that causing problems with switches that are, you know, not not designed to operate with that particular sequence.
Yes.
But one thing I found with switches is that you usually need to kind of force it into. They usually don't do a lot of auto negotiation. You got to force it into the right state usually. So like if you're trying to, you know, run an FPGA connected to a switch at 25 gig through a 100 gig port, you'll have to force it into 25 gig mode or force it into 4x25 mode, because by default it built and runs at 100 gig. So I don't know, not really a major deal or anything, just kind of an observation. There was somebody asking about that on the Corundum Slack channel just a couple of days ago, trying to get Corundum talking to a switch and trying to figure out, okay, how do I need to configure the switch port? Yeah, auto negotiation off, switch to force it to 100 gig, force it to a particular FEC mode, and then it works. It's like, yeah, okay. With a Mellanox stick, you plug it in, it just works. It's like, all right.
Yeah, and to tell you, we've seen similar even within our own product, believe it or not. You know, like one of our NICs, the X25 or the X100, and even with our own switch, we have to set some certain parameters. We did when it first came out. I think it's fixed now, but yeah. So we've seen similar things.
Right, yeah. I mean, to some extent that makes sense, right? You plug in a 100 gig DAC, the switch says, oh, I'm just going to run a 100 gig because it's a 100 gig DAC. Well, it's not always the right decision. Anyway, but yeah, I guess one thing you could have with DACs is like the other end of the 100 gig DAC might be plugged into a 40 gig NIC. So if the switch tries to bring it up 100 gig, you get no link. But I guess the other thing that could happen if you're not looking at the cables, then you can plug in a 40 gig cable between 200 gig ports and then have the link be kind of iffy because the cable's not designed to go that fast. We have a bunch of 40 gig cables in one of our test beds UCSD, and that always causes problems. They're like, why is this NIC only running at 40 gig? Oh, the cable's only 40 gig. Somebody's got to go in and shuffle some cables around. Anyway. Anybody else have any questions or comments or anything?
Maybe two.
Okay.
First is, I guess, DPDK. So we had some recent advances in the DPDK driver.
Okay.
So we adapted it to the current register layout.
Oh, nice.
And we are now able to provide more than a single port, but each port is now available in DPDK as well. So we're currently cleaning stuff up and yeah, will provide a new public push for this. The other thing is that we also are now working on exposing multiple queues, which is a little bit different. So we now also update to a newer version of DPDK to be able
So
to
this
use
is in the
multiple queues per
DPDK driver, right?
interface.
Yeah, okay.
Exactly. Yeah, so DPDK handles queues differently than the Linux driver. So the old way in DPDK was there's a single queue per interface. And you could do custom stuff to support more queues. But in the newer versions, that's like more regular use case to use multiple queues. So that's what we're currently updating to, I guess, some 21 dot something release.
Wow, they only added
And,
the queues that recently. That seems like a very natural thing to support because the NICs have multiple queues. You might as well have a good API for that. The NIC only has one queue,
Yeah.
then you only expose one queue. But if you're going to limit it to one queue, that's like, okay.
I guess the difference is that now multiple queues can be used in default configurations. So in the past, there were some more custom things needed
Right.
to make use of them. But yeah, so I guess that will be provided in the next weeks, I guess.
Well, that's good to hear. I think there's a number of people in the Corundum community that have been, chomping at the bit to try
Right.
out DPDK. So, yeah.
So I guess now we are
what kind of bandwidth are
approaching
you
a
testing
state
that
that
at? Are you
makes
just
sense.
testing it mainly on your custom hardware, or are you also testing it on some higher end stuff? Like, can you get 100 gigs?
Yeah,
Or,
that's what we are start testing right now. So we did just functional tests as of now.
Right.
Like, yeah, we are getting packets in and out, and they make sense and so forth. And now we are running. So we only have 10 gig designs for currently, I guess. So we are mostly testing 10 gigs, but multiple 10 gigs ports in parallel.
oh, right. Okay.
But I guess we have one Alveo somewhere lying around, which we can build a design for and then test at 100 gig as well.
But didn't you say you also had those like Sidewinder cards or something? I think those
Yeah,
are also
but
100 gigs. So
yes, from a physical perspective, but our designs are 8x10 that we use for
okay, I
testing.
see. You haven't made a 100 gig design for that. All right, fair enough.
Right. So yeah, but yeah, we could also use this as well. Yeah. But
It would
yeah,
support it. You
as I
just don't have a design for it. Yeah. Okay. Yeah. If I had a
Exactly.
Sidewinder card, I would definitely have a design for that in the upstream repo. But until I get a Sidewinder card, that's not going to happen. So.
Fully understood. Yes.
And I guess the other thing that, speaking of that, the Sidewinder card is one of the zinc parts, right? I think it is.
Yes, it is.
Yeah. It's not,
ZU19.
not a standard
yes.
FPGA. Yeah. So that's got me thinking because I have support on the bitware 250 SoC, right? Or the SOC 250. I never remember what the part number this is. It SOC 250 or 250 SOC? It's 250 SoC. Yeah. So this one also has a zinc ultra scale part on here. Oh, small note that is kind of interesting. I was looking at the floor plan of this, and as far as I can tell, it is identical to the KU15P. I think they used the same silicon for both. Interesting.
Awesome.
I didn't realize they would do that. Zinc and the Kintex ultra scale, same silicon. So they must turn off the ARM cores on the Kintex part. Anyway, it's got me thinking about if you have the hard ARM cores on there alongside this big honking PCI Express interface, what can you do with that architecturally? Kind of food for thought, because it seems like you could almost make sort of 3 different versions for this, right? Because like on the ZC106, I have a PCIe version and an ARM version. For the PCIe version, talks to the host over PCIe, and the ARM cores are doing nothing. And then the ARM core version, the ARM cores are used to interface with Corundum, and the PCIe interface is doing nothing. Well, you could make potentially a third version that uses both in some way. I'm not sure how that would work right now, but that's potentially something interesting to think about.
Like you could do for example, having an application run on the zinc. So
Well, right, yeah. So you can have kind of your main interface, the high throughput connection over PCIe to the host, and then have the ARM cores be able to do something. It's a question of how that would be integrated into the rest of the system, and I don't have a good feel for how that would look right now, but something to think about. Because that could be an interesting design to put together, and then we could run it on the 250 SoC on the Sidewinder, and potentially also on the ZC106, and that could potentially open up some interesting directions. Having all of those cores available makes it potentially a little bit closer to some of the other smart NICs that are out there. Where they give you a bunch of ARM cores on the card.
And it might be interesting to have some applications fully implemented on the card, even if there is software involved.
Right. Yeah.
Exactly.
So that could be a little bit of food for thought. Anyway, you were saying, is there anything else from MLE's end?
Yeah, the second thing was, I don't get it anymore. Timing. So in the past,
yeah,
we
there's a lot of
some changes for the ZX 10, right?
Right.
Did you have the time to look at them already?
Well, so you have that pull request, and that has some modifications not only to Corundum but also to some of the supporting libraries as well. So yeah, I took a look at that a while ago. I think there's nothing really wrong with the changes. But I think some of the changes in some of the AXI components I was thinking about implementing in a slightly different way. I just haven't had time to sit down and take a look at those and sort that out. So because that has changes for multiple repos, I'm not really going to pull it into the Corundum repository. But my thought was to potentially do a once over on some of the supporting libraries and apply some of those changes, more consistently across some of the other modules. So I think you had some changes for the AXI Lite crossbar, but I think the AXI crossbar potentially needs some of the same changes and a couple of other modules. So I just haven't had time to really sit down and turn the crank and apply a lot of that stuff. So what I'm hoping to do is once I get the let's see, I'm finishing up the shim stuff and the flow control stuff now. Then the next thing is variable length descriptor support to get that operational. And then after that, I need to get timing closure on the 520N MX. And I've definitely seen a couple of paths failing on there, and the couple of times I have done test builds that seem to match some of the changes that you guys have made. So once I'm in that stage trying to get everything running on that card, then I'm definitely going to be taking a look at getting all of these changes merged in and applied properly across everything. So
yeah, no worries. So if there are some questions, just reach out to us, and
I will absolutely reach out to you guys if there's something weird going on. So
and
the one thing I have not tried yet actually is that whatever it was, QSF setting to change the RAM inference. I have not tried that yet.
Right.
I need to do that and just see what happens.
Yeah, so it helped us quite a bit.
Yeah. I would believe that.
Yeah, and just to let you know, we are still working on timing. So there will be another set of patches provided at some point.
I mean, it seems like you guys have been doing a lot of work internally. I just I was expecting to see another pull request or something with some, or an update of that previous pull request or something. So, but I don't know. I guess you probably have a lot of organizing to do internally. I know with timing changes, you never really know what a particular change is going to do in terms of improving the timing or whatever. So it takes some time to kind of go over those with a fine-tooth comb and make sure that all the changes you're making are actually improving the timing and having a positive impact.
And not breaking functionality in the same time. So
well,
I guess
breaking functionality is one, but some of these changes, it's you're trading off maybe a few additional resources for potentially shortening the critical path and improving the timing performance. But if it doesn't improve the timing performance, then maybe the higher resource consumption is not something you want.
Exactly.
So,
Yeah.
yeah. Yeah, I
Yeah.
did do
So
a bunch of
I guess you
hammering
have.
on, right, so I did do a bunch of hammering on like the Ethernet MAC and some of the PTP components. I mean, I guess if you're not using PTP, then maybe that's not really going to make much difference. But the newer Ethernet Macs, I think, have improved the well, I don't know if they've improved the footprint much, but they've definitely improved the timing performance a little bit. So if you're using my Ethernet Mac, definitely take a look at the latest one because
Yes, we do.
that might improve things a
Okay.
little bit.
Okay, cool. Good to know. So I guess so we are currently in a phase where we kind of finalize things. So we're a little bit slow with picking up changes, I guess.
Right. Yeah, it's not
Because
surprising.
so we are working on a lot of like all these tiny bits and pieces that is kind of loose ends and tighten them up and then getting release shipped.
Right.
And we're still bringing up some hardware. So the Intel board has been brought up, and the next revision is on its way.
Okay.
But
Oh,
yeah.
so you had to do a hardware revision. Okay.
Well, yeah. So not for FPGA reasons, but yeah, power supply stuff mostly.
Not surprising.
Yeah, and
I've just
so
been
from
looking
a
at some of
functional
the
perspective, everything
FPGA
was
boards
working.
that I have here, just in terms of the complexity of the power supply on there. It's like I don't know how they
Yeah,
got that right the first time. They probably didn't.
maybe. So at least we got everything working that we had to. So that's pretty good. First shot was okay. So we are mostly happy with it. But there is another board waiting to be brought up completely. So yeah,
Another.
there's a
So this is
focus
the
on this.
revision 2, or this is a different thing?
Completely different, more embedded type of board.
I see. Oh, is this the Zinc version of it?
Right.
Ah, okay, okay, I see. Well, hopefully Peta Linux doesn't cause too much trouble.
Not yet. No, but actually it's the same Zinc Ultra scale that we already use, so I guess that it should be okay.
Right. Right. Okay.
PHYs are getting into our way, but that's what they do.
The which?
PHYs, Ethernet PHYs. So we're
Oh, the
using
Ethernet
1
PHYs.
gigabit Ethernet PHYs on this
Ah,
one.
the PHY chips. Yes, yes, yes. Okay, yeah.
Yes.
Ah. Were you
Always
guys
the same
using some
thing.
like a QSPI thing or something, or not QSPI?
We wanted to use
QSGMII?
QSGMI, right? And that's, I don't know.
That wasn't working properly or something?
Well, no, actually, no. So the Guidance IP course says something like, so we tested it in simulation. And then at some point, he just gave up.
Well, okay, that's a pain. So you're using a different.
Maybe we will visit it later on again. And now we are using just a lot of SGMI interfaces.
I see. Can you run
So
that off of
we
the
had
normal
this-
I/O pins, or are those fast enough on those modules, or do you have to use the serializers?
Actually, I'm not sure. So we do use the GTHs for this.
Ah, okay,
So
okay.
they were enough. And so for QSGMI, we had to use them anyway. So they were connected. So power and clock was available. So we just connected more lines. Yeah, didn't.
Yeah, because I just know
think...
on some of the larger Vertex UltraScale dev boards, they have the an SGMI PHY wired to just normal I/O pins, and then they use
Right.
the bit slice primitives and whatnot to run those at 1.25 gigabits per second. So
yeah,
which is
and
cool
our
because you can
thoughts,
hang some stupidly large number of PHYs on there if you really wanted to.
if you
Because it
have a
doesn't use
stupidly
the
large
receiver.
FPGA to implement all these files, yes. But yeah, you need to do 8B, 10B coding and soft logic then, and now we use the
Well, yeah, I
one
mean,
present.
the point is it only takes like what 6 pins or something per PHY, something like that. If you have
That's
the
right.
the separate clock signal, so you have 500 pins or something like that, so you can easily put 100 PHYs on there if you wanted to, approximately.
Yeah,
So,
that's right.
Well,
Yeah,
I don't know about easily, but you could
exactly. Yeah.
without using any of the serializers. So
Yeah, not sure how is it called? This simultaneous switching limit says about you using it this way, but yeah. So there is always interesting
well, if they're all in,
requirements.
so if they're all in LVDS mode, that might not be an issue, right? The simultaneous switching limit stuff, if it's all single-ended, then yeah, that's a problem. But the LVDS stuff being differential, I think those limits apply differently.
Yeah, I never looked at it.
Yeah.
You don't know. So if we would do such a board, I would definitely read more about it.
Yeah. Well,
Um,
so the big gotcha with that though is that the way the bit slice primitives are set up, they are extremely sensitive to exactly which pins you're connected to. So that's the kind of thing where you definitely have to do a test, a test build with the exact pins that you're going to use and make sure it builds correctly. Because when I was trying to get like the VCU 108 and the VCU 118 worked up and running with those PHY chips over SQMII, I had to go through several iterations of getting settings correct. I mean, the pins were correct because this is the board from Xilinx, but you have to make sure that the settings on the PCS PMA IP core on the FPGA matches how the pins are wired up, which is annoying to say the least. And it took a few
Yep.
iterations to get that right.
Yeah, and that's not so nice to debug.
Not so much, because you get some really unintuitive error message if those pins are wrong. It's like everything works and then it fails DRC, and it's like, why? Anyway, enough ranting about the tools. But what's new?
At least sometimes it helps us to get some, I don't know, fun, but it doesn't help improving or sort out problems.
Well, I mean, sometimes an issue that somebody's run into, just being aware of it, can help somebody else,
oh
not
yes,
fall into the same hole and then have to
Like-
respin a board.
like your 22.2 problem.
Mhm.
Help
Yeah.
us to know this.
Like, oh,
Yeah.
that doesn't work. You can't build the design because it doesn't even
Mhm.
check the timing.
Great
Oh
stuff.
man. Like, hey, you build it. Hey, close timing. That solves all our problems. No more work on the timing optimization if you don't check it right.
Mhm. Yeah, that really doesn't
Oh,
make
boy.
sense. There was one question still left.
Oh, okay.
Yeah, right. I guess last week, Joachim brought this topic up about the LED things.
Oh, right. Yeah.
I don't know. So I actually didn't look into the record of the last meeting.
Right. Yeah. Okay. So
I'm not sure if you had some
Joachim
thoughts about
was
that.
suggesting about adding some potentially standard registers for LEDs down in Corundum that we could then connect to lights on the board. But I'm not sure what the best approach is going to be, because some boards don't give you any LEDs. Some give you like one LED per QSFP or something stupid like that, as opposed to 4 or 8 LEDs per QSFP, which is much more reasonable. And then on some boards, the LEDs are accessed in weird ways. So I know on one of them, I had to write a little shift register module to shift the LED states out into shift registers that drive the actual LEDs, but that's a really relatively minor thing. On a bunch of the Intel dev boards, though, they use these like QSFP management chips, sort of, which sit on I2C, and then they have an I2C connection to the QSFP, and they have several LEDs connected as well. So all of the LED state changes have to go over I2C through these chips. So that does raise the question of, okay, if we're going to connect LEDs up to this thing, how do you do that? And from my point of view, there isn't a really clear answer. So I was almost thinking with the LEDs, you could handle those in the soft core and maybe have some registers the soft core can look at in terms of, looking for activity on the various interfaces. And then,
Okay.
the soft core would know how to map the interfaces onto the LEDs. But we don't have a soft core running yet, so that doesn't really help you guys at all.
Well, yeah.
And then the soft core could also talk to these, interface chips, right? So, yeah, I don't know.
Yeah.
LEDs, complicated problem to solve, annoyingly enough.
Yeah, really. So what I thought about is just provide a kind of simple interface, like
well, what might make more sense is instead of having like LED outputs, I could definitely see putting in some connections for like activity, link status, and maybe a couple of other things. I mean, the other thing is some of the link status information is going to come from like the PHYs, right? So if you wanted to indicate what the link speed was, that doesn't come from down inside of Corundum. That comes from the PHY, right? Or the Mac maybe. So, adding something to the Corundum core logic isn't going to help you with regards to that. So,
well, at some point, I guess that's information that somehow you want to report, don't you? So I guess
reporting at the driver level or whatever. Right. Well, the other issue is, how are you going to collect? Right. Well, the other issue is how do you collect that information as well? And that could be very different depending on what device you're on. Like some of them might expose it on pins. Others, you might have to read it out of registers or something. So a lot of this kind of management level stuff I was thinking about softcore. And the softcore can do the appropriate board, PHY, whatever specific thing. And then the driver can use an API to talk to the software and read that information out.
I guess there's two things. So one is usually network cards have an ETH tool interface to, for example, actually switch LEDs on to kind of say, if you're standing in front of the server, use this brightly lighted thing and connect something there. I guess that's the idea. Some operator going through the server aisles and saying, okay, I have to connect a new cable somewhere. Please tell me where. So that's where you definitely need some API for the software to talk to. So that might be a register interface or whatever different API to a software possibly.
Right.
And then I guess there is another thing. I don't know if we discussed it in this round already, but internally we had some discussion about this definitely in the past, and that's how to represent these PHY level information, right? So there is some, Corundum does have some PHY implementations, and usually there is some hooks in the drivers to interface to them. And I guess we're kind of missing this. So
you're talking about like the interfacing with PHYs over MDIO, or like a register interface to a PHY, or what sort of information?
More like a driver API. So usually you assign.
So this is to like report the link speed and whatnot.
For example, right? Exactly. And I guess that the LED information would also kind of belong to this.
Right.
And I guess Joachim knows a lot more about this, how this is actually done in the Linux kernel than I do. But I wrote at least one PHY driver,
really.
and they definitely have some hooks.
Yeah, the point is that the Linux kernel has I would say, a generic framework for representing PHYs. And this is not only for network interfaces, but for other stuff too. And what exactly they do, I cannot say, but thinking about it, I would say it's likely that all sort of things related to a PHY can then also be exported by such a representation in the operating system. And then there's a binding framework, which where, for example, a NIC can say, I want to access my PHY, and it's kind of a standard interface, a standard connection in terms of software, in terms of management in software. So from the operating system point of view, there's a NIC, a PHY is attached to it, has certain properties, has a defined interface abstraction to the hardware, whatever the PHY can do, and so forth. And I mean, that's certainly not a new thing in the Linux kernel, but it's not like, I would say, 10 years old or something like that. And I think that a lot of stuff is moving into that direction. I've seen that with USB, for example. USB usually also has something like a PHY. And so from the operating system point of view, there are two components. It's the USB controller on the one hand and the PHY on the other hand. So it's coming from that direction, representing hardware in the operating system in a more fine-grained way, you could say. And this applies to obviously network devices and other stuff too.
Right. So you got the software level API, and then I guess the question is, how do you get from the software level API to the actual hardware components?
Yeah.
Yeah. So the reason I haven't done much of this so far is because, you know, it's not part of the data path. The thing will work without implementing this. But when you start getting into the management nitty gritty, yeah, I can definitely see how this is going to be important to implement on some level. But the trick is, you know, how do you do that in a way that's going to work across, you know, all of the various target boards without having to make extensive driver modifications and whatnot to support, you know, new hardware. So yeah, for things like this that are what I consider to be kind of management level features, my, you know, kind of default is to say, well, maybe we should implement this in the little management software. Once we get that running, then we can implement, you know, some sort of mailbox style API, and then the software can perform the, you know, board appropriate, configuration appropriate operations, you know, to satisfy the request from the driver. Because otherwise you might end up having to, you know, write a bunch of, you know, board specific code in the driver, which there is some of that now, but I'm trying to get rid of it. So yeah, what the most appropriate technique is, I mean, I guess it would certainly be possible to implement, you know, some other interface and then, you know, deprecate it once we have the software working, or, you know, if you don't have the software set up, then you can use some other interface, but I don't know. I mean, yeah, pragmatic solution, if you wanted something working now, since the software isn't set up yet, you know, maybe having something that can be done just on some additional signals pulled out through the core logic, you know, maybe that could make sense. Well, I guess the other thing is that on a fair number of boards, you know, there's some, you know, board level components that are not pulled out through the hierarchies, like the I2C interfaces and whatnot, and the, you know, module control pins and whatnot. Potentially, you know, you could implement something there for the time being. Do it in a board specific way, and then once we have the software working, then we can, you know, push that functionality into the software. Yeah, I don't know. To be honest, I haven't spent a whole lot of time thinking about it because I've been working on the PCI Express interface.
No
yeah,
problem. Just
making
wanted
the
to bring it on the
LEDs
table.
blink with link traffic and whatnot, I think would be a useful feature to have. It's just you know, we got to figure out the details of how that's going to work.
So that's already in place on our card. The question is just if and how to put in a register interface for it.
So
Not
we
a
have
friend.
it currently hard coded. That's what Uli wanted to say. It's hard coded that a certain LED is indicating traffic, another LED is indicating link up. And we talked about that last time, and we envision a kind of a small register interface where it's possible to say where, okay, there has to be an association between a port and the LED, which has to be done by other means. It's not the business of the driver in our vision here. The port offers an interface, and for an LED, or say, let's say 2, 3, or 4 LEDs, and software can then say, okay, LED number 1 should have a special function called show traffic. And LED number 2 should do special function show link up. And LED number 3 is, I don't know, software controlled by ETH tool, for example, or any combination of that. So rather small, a limited interface, which we think, could be at least a stopgap solution until the management core is there.
Well, I mean, the simplest stopgap solution is we could just implement, some registers at the board level, corresponding to those LEDs, and then, the driver can poke the appropriate ones. And then if we need to have some feedback from elsewhere in the design, so it's like, link state, link up, link down, that doesn't even necessarily need to go down into the design at all, because, you have the port, physical port, you have the PHY, you can just directly connect it to the appropriate LED. I guess the question is for things like for traffic, potentially you could pull that out of the PHY, or potentially you could pull that from deeper down in the design. I'm not sure where it would make sense to monitor, traffic on a link.
Well, actually, I just used the right in front of the file. So I put it in the port level actually right now.
Yeah.
And so it's inside Corundum, I guess. I use the TLAST signals behind the place where the data paths, so the transmit data paths of the app and the interface get merged.
Right.
Because that's the next thing. You have multiple data paths in parallel going to the Mac. And at some point, you want to capture all of these because all of them may generate traffic.
Right.
Yeah. So that's what I used to check for activity. Yeah, and the link up comes from there anyway. So that's already present.
Well, wouldn't you be capturing the traffic at the Mac?
Yeah, that where I hook up it's directly in front of the Mac, I guess. So that's just
Right,
wires
okay.
until hitting the Mac.
Right. And then you're just looking at the TLAST to indicate that you have something going on there. Yeah, I guess you could use
Right.
TLAST, or you could even just use TValid, I suppose.
Yeah, kind of isn't.
Doesn't make that much difference.
One of those, right? Yeah, but as you just require a pulse, either is good enough.
Right, yeah.
Okay.
Yeah, okay. Yeah, and then I guess from that standpoint, you also have the link status feedback as well, right? Okay, so you do that, then you generate the LED states, and then I guess you're saying that it's up to the board level code to connect that to the appropriate LED.
Exactly.
Yeah, so I guess that works as long as you have at least one LED per port.
Well, you can somehow max or do whatever on the board level again. So what my approach now, or our approach now, let's better say it like this, is we support up to 4 LEDs per port. So that was the idea with the register interface that we had, and we didn't implement the register interface yet. So that's just there as sitting there as a proposal.
Right.
But so we do have 2 LEDs per port on our card.
Right.
So that's what we have in place. And we were thinking about, okay, let's say maybe you have 4 LEDs because more is unlikely, I guess. So there is limited space in the front bracket. So having like 2 dual color LEDs is pretty good actually.
Right. Yeah, that to be honest seems pretty standard. So I sent a link to a data sheet around last time for this little QSFP control chip, and they support 4 LEDs per port. So, you know,
Okay.
you guys aren't the only ones coming to that same conclusion. So
yeah, so then that was the idea, and then yeah, you basically usually have like these 2 states, right? There's link and there's activity. Maybe there's a speed, and that's the next thing.
right.
So link speed. I don't know anything else. Yeah, you could do some custom things. So if you have an application in place that might be switched on or off, you may want to reflect this state as well. That could be thought about. I don't know. And then there is like, we push through these these array vectors to the hierarchy, and on top there it's actually connected to a physical LED. So that's not part of the port logic, right? It doesn't know if there is an LED and how it is used. It can just provide the information and the state of this LED, and if it's actually brought out to a pin or maxed or serialized or whatever, it doesn't know about this, and it doesn't need to know about this. It's the same with a lot of Ethernet PHYs do the same. So the PHY we use here on the other board is doing exactly the same. There's 4 LEDs per port, and internally you can access these states, but externally via direct I/O you just have 2 pins. So you can only drive 2 LEDs, but each port generates states for 4 LEDs, and you can select about which modes of operation you want to have on which LED. And taking this approach, yeah, we sketched out a register layout that also reports the availability of LEDs. So if an LED is not available, software might want to know this, right?
Right. Okay. So what do you do in a board that has the LEDs sitting behind these, you know, QSFP control chips?
Now, then you could, for example, go ahead and say, okay, you have something talking to this chip. I don't know, it might be the soft controller, the soft core, and it might hook up to the LED output and translate it into whatever is required to operate the LED.
Okay, so
But-
in that setup, you would have the soft core read these read those output pins basically, and then
Right.
forward that in some way to the control chips.
That could be the representation to the API. If it's actually the implementation in the logic, that might be something different, I would say. But this way, you are kind of also decouple physical connectivity of the LEDs to creation of this port status, let's say. So there's
Right.
like, you have four signals that you can use to move around information about port status. You can select the modes they are operated on, and then on the top or higher layer, you can select how to bring them out, if you're able to bring them out. Maybe you don't want it or whatever.
Okay.
And you can always read the status via API as well, so via the register as well. So that was the idea. Well, I do get what you're saying about the soft core. That also makes sense. Yeah, not sure. I guess maybe we have to think about it once more.
Because I'm thinking if you're going to make the muxing board dependent, do you really even need, you know, registers at the port level to control stuff, right? Because you could just pass these various status signals directly. And then at the board level mux, you have your TX activity, RX activity, identify light signal, speed, which would be coming from the phi, I guess, not from down in the design. And
Yeah,
then you
but
can mux those.
if you think from a software perspective, you somehow have to hook up to this. Somehow have to expose where to look at. Right? So I don't know. You need to have this connectivity between this hook from port to register space. I guess that's possible, but I don't know. It was straightforward to put it into the port.
Well, some things definitely make sense to put into the port. Like if you wanted to do some port ID thing, maybe it makes sense to do that there.
Okay, so basically,
I think we're
the
definitely
idea
getting
would-
into bike shedding territory here.
yeah,
How do we wire up the LEDs? Let's discuss that for an hour.
yeah, okay. Let's stop this discussion. I guess we
No,
presented
not
two
necessarily. I
two
just
approaches.
think it's
and
funny.
let's see. No, I guess you're right. We don't need more discussion right now. I guess that's just bumping ideas.
Bouncing around ideas. What's the best way to build it? Well, it's probably like 10 different ways you could build it that would all work just fine.
Yeah,
Yeah, I mean, I'm just thinking if you're doing
something-
any kind of reconfigurable board level muxing, you're going to have to expose that somehow.
Right.
And that wouldn't go in the port because it's board level. So, but yeah, I mean, I can also see the argument for putting stuff at the port level. Yeah, it's definitely convenient to have it there because then bang, you immediately get it for all the boards. But it's
or maybe
just on.
that's
Hmm?
we should just kind of postpone this and have a look at the driver level phi integration perspective.
Well, yeah. Why don't you post some links in the Slack about the phi level registers, because I'm not even sure exactly what knobs you have at the software level. And
Yeah.
I can also send you guys the documentation for that TI part.
Okay.
Because talking about just for controlling LEDs, they have some gigantic programming manual for that thing. Well, it does more than just controlling LEDs. You can do it's designed for like switches where you have a whole bunch of modules and maybe you only want to hang that off of one I2C interface or one SPI interface. So it's got a whole bunch of like address auto detection stuff, and even has some ability where you can like queue up writes to QSFP registers and then fire them all off at the same time, or doing broadcast writes. It's got some other weird stuff in there.
Okay.
But
Sounds
just
like
at least in terms of looking at what the LEDs can do, I think it has like some sort of PWM support and a few other things. Yeah, I have not taken a super close look at that, but yeah, they do have a pretty extensive programming manual. So I'll post that so you guys can take a look at it, and maybe there's something interesting in there. Maybe it'll give you some ideas, maybe not. So because this is what most of the Intel boards have for whatever reason, right? The Stratix 10 DX dev kit has that. I think the Stratix 10 MX dev kit might also have that. Yeah, it's like there's several boards. I'm like, I was going to implement an LED, but nope, you can't actually talk to any of the LEDs because of this darn chip in the middle. So, or actually, it's also the QSFP communication goes through this as well. So I think it does like some address translation, because all the QSFPs, they always sit at address 50. So if you put too many, you can't put more than one on the same bus. But with this chip, you access a different I2C address and it gets a map to 50, so you can access the QSFP. Anyway, yeah, we can go ahead and post the the documentation. I'll post this. You guys can post the API docs, and then we'll go from there. All right.
Great, sounds good.
Okay. Does anybody else have any questions or comments or anything? Any ideas on how we can make more LEDs blink in interesting ways? Just reminded myself of the Dini group that they made some really big FPGA boards for ASIC emulation and other stuff, and they always had the most hilarious descriptions of, you know, this board has enough LEDs to hypnotize a trout or something like that. I said some really funny thing in their documentation somewhere about the number of LEDs on the board. Anyway,
They had a lot of funny documentation anyway.
yeah, the Dini group guys had a good sense of humor.
Mhm. There was one documentation that mentioned, I don't know, some high score levels in some online games of the developers of the board. Like, okay, what
I
has
wonder what
this
they were
to
doing
do
at
with
work.
with the accountability of this board? Do I trust it when they do more gaming than developing? I don't know. Maybe they are so good that they have so much time for gaming. Yeah, that's also possible.
And their code names are also pretty funny too. Anyway. All right. No more questions or comments or anything? All right. Well, I guess we'll go ahead and adjourn for today, and I'll talk to you guys in a couple of weeks.
See you in 2 weeks.
Sounds good.
Thanks,
See ya.
everybody.
All right, bye.
Thank
Thank you.
you. Thanks, everyone.
Bye.